Okay, so now using the same variational arguments that we employed in the case of nonlinear elasticity, we can separate out the integrand here. Okay, since it must hold for all w belonging to V, what we say is that also holds for W which is equal to mu, right, the chemical potential itself, times a function chi of x, where chi of x is greater than 0 in omega. Okay? All right? That's all we require. On the interior of the body, chi should be greater than 0, any kind of function. We don't care what it does on the boundary, okay, in this case. All right? We don't necessarily care what it does on the boundary, but of course we know that W must vanish on the displacement boundary. Okay? So we force that condition. And this thing should be equal to 0, not on the displacement boundary, sorry, I misspoke, on the concentration boundary. Okay? Because we know that we have that condition on W at the concentration boundary. Okay? What this gives us then is that integral over omega mu square chi dV equals 0. Observe that there are no boundary terms in this expression. Okay? Since chi is greater than 0 over the domain, all right? If this is, and mu square, being a square, is always greater than or equal to 0, the only way this condition can be satisfied is if at equilibrium, mu, which we've decided is the derivative of chi with respect to c, if this is equal to 0 in omega. Okay? This is the condition for chemical equilibrium. Okay? All right. Now, here's the twist. The problem of mass transport is one at which we are not at chemical equilibrium. Okay? The interesting part of mass transport is when we are not at chemical equilibrium. Okay? So what happens then? Okay? What about the regime far from equilibrium in chemistry? The reason this is more of interest is because when things are at equilibrium, nothing is changing, right? So there's really nothing happening with chemistry. In fact, there is no transport. Okay? Nothing is changing, right? So our derivative with respect to C also vanishes. Okay? All right? So let's just state this. So chemical equilibrium implies this is not of interest, okay? Because then if you look at our mass transport problem, it can be satisfied quite trivially, okay, with the zero source, okay? So this would also have to imply that our source pi for mass transport also equals 0. This is not of interest so much. We really want to look at things that are far from equilibrium. This takes us into the domain of non-equilibrium thermodynamics for chemistry. Okay? This takes us into the field of non-equilibrium thermodynamics. okay? And that is where we write down the flux. In the context of non-equilibrium thermodynamics, what is done is to say that the flux is equal to minus the gradient of the chemical potential, and we want to have some material constant, okay, or some material parameter in front of it. So typically we will say that there is a mobility tensor. M is the mobility tensor, okay. So J equals minus M gradient mu, where M is the mobility tensor, okay. The motivation for this sort of a constitutive law, okay, and this is our constitutive law. The motivation for this is the following. So if we have our body omega, we're saying that suppose you have mu here, right? Suppose you have mu at a point x1 and you have another point x2, right? So we have mu1 and mu2, right? Let us suppose in this setting that let's suppose that mu2 is greater than mu1. Okay, or because of the way it appears on this slide, let me make it the other way around. Let me make it mu2 is less than mu1. So mu1 is greater than mu2. Okay. What this tells us is that because mu1 equals derivative of chi with respect to concentration at x1, and mu2 is derivative of the chi, the free energy density function, with respect to concentration at x2. Okay? What it tells us is the following. What if mu1 is greater than mu2? It says that for every little bit of concentration or little bit of material that we add at the point x1, the free energy change is greater than if we add the same amount of concentration at the point x2. Okay? So in some sense, this says that the point x1 is energetically more expensive than x2 because delta chi, which is delta chi at x1, which is mu1 delta c1, is greater than delta chi at x2, which is mu2 delta c. So actually I should make the two delta c's the same. If you add a certain amount of material at the point x1, you increase the free energy more than if you add the same amount of material at the point x2. Okay? And you recall that there is this tendency for physical systems, which comes from the second law of thermodynamics. There is a tendency for physical systems to decrease their free energy. Okay? Because there is a tendency to decrease the free energy, which comes from the first and second laws of thermodynamics, the point x1 is energetically less favored by the laws of thermodynamics. Okay? So, let me go to the next slide. Since free energy is non-increasing for closed systems, okay, x1 is not favored over x2, okay, and this result comes from the first and second laws of thermodynamics. It's actually something that we derived when we treated the problem of thermomechanics. Okay, we derived this form of the combination of the first and second laws. Okay, so to go back to our picture, we have x1, we have x2. We know that mu1 is greater than mu2. So what can we do about this? What we can do is move material from x1 to x2. All right? What you want, but then movement of material is flux. So you want the flux to go from x1 to x2. Okay? And that is essentially what we get when we say that the flux has to go along the negative gradient of the chemical potential. Okay? These two parts, the negative gradient. For this to work out, M is positive semi-definite. Okay? That is what ensures that the flux will go from x1 towards x2. Okay? And this is the motivation then for our flux law, for our constitutive relation for flux. Okay, so to complete the picture for mass transport, we have our PDE for mass transport. Which says that partial derivative of c with respect to time is a source, if we have a source, so we're supplying this material at every point in the body, minus divergence of the mass flux. Boundary conditions are C equals C bar on the concentration boundary or the Dirichlet or essential boundary, okay, and we have minus J dot N equals J bar on okay. We have initial conditions, or we have an initial condition, okay, IC for initial condition, which is that C equals C naught at time t equals 0. Okay, and then what is J? Well, we've just identified J to be minus m, the mobility tensor, grad mu, where mu is the derivative of the free energy density function with respect to concentration. Okay, that completes our basic picture for mass transport in the continuum setting. When we proceed with studying mass transport, I'd like to go ahead and consider a very special type of mass transport, which is something that governs processes of phase separation. Okay, so we'll look at that when we come back later.